Energy is everywhere around us. But here's the thing, energy never just disappears, it constantly transforms, transfers, and sometimes getting a bit lost along the way. Today, we'll dive into one of physics' most fundamental laws and discovering why your phone gets hot, why car brakes warm up, and why that bungee jump doesn't quite bounce back to where they started. Let's start with the basics. Think of energy like money in different bank accounts. It can be stored in various ways. It can move from one account to another. We have different energy stores. Starting with chemical energy store, like the fuel in your car or the food you ate for breakfast. There's also kinetic energy, that's the energy of movement from a speeding bullet to a gentle breeze. We have gravitational potential energy that is stored in anything above the ground level. The higher an object is, the higher its gravitational potential energy. Then we have elastic potential energy, that is the energy stored in stretched or compressed objects, rubber bands, springs, even the ground you step on. And then we have thermal energy, which sometimes we call internal energy depending on the application. That's the energy stored due to temperature. Well, here's where things get really interesting. Energy loves to move around. In a simple touch, chemical energy from the battery becomes electrical energy flowing through wires, which then becomes light energy and thermal energy. Yes, that's why your touch gets warm. When you boil water in an electric kettle, electrical energy transfers to the thermal energy store of the water and the kettle itself. The energy isn't lost, it's just changed form. The principle that rules the entire universe, which is the law of conservation of energy, that is, energy cannot be created or destroyed. Full stop. End of story. That's the law of conservation of energy. And yeah, it's more reliable than your morning alarm. Watch this ball being thrown upwards. As it rises, it slows down. Its kinetic energy is decreasing while its gravitational potential energy store increases. At the very top, it stops for a second. Maximum potential energy, zero kinetic energy, then gravity takes over and it falls. Potentially, energy converts back to kinetic energy. So the total amount of energy never changes. It just moves between different stores, chemical, kinetic, gravitational potential, elastic, and you name it. This brings us to one of the most thrilling examples of energy conservation, that is bungee jumping. As our daredevil jumps, gravitational potential energy converts to kinetic energy as they accelerate downwards. When the bungee cord tightens, the kinetic energy transfers to the elastic potential energy of the stretching rope, bringing them to a stop. Then the rope recoils, converting that electrical energy back into kinetic energy, pulling them back up. Sharp-eyed viewers will notice our bungee jumper doesn't return to the starting height. Yes. Where did all of that energy go? It didn't just vanish. No. Remember, energy cannot be destroyed. So where did it go? Well, it is dissipated. It was dissipated to the surroundings, lost to the surroundings in form of thermal energy. Well, if there's a way for you to get all of the thermal energy back, yeah, you have your energy equal, from what you started with to what you ended with. But yeah, we're gonna get all of the thermal energy back. It's in the surroundings. During the jump, some energy transfers to the thermal energy stores of the rope, the air, and the jumper through heating. Some escapes as sound waves, that whooshing noise, and the jumper screams. The energy has spread out to the surroundings in less useful forms. You can feel this yourself. Rub your hands together vigorously. They get warm, right? You're doing work to overcome friction, and that energy is being dissipated as thermal energy. This is why moving parts in machines get hot. Friction is constantly converting useful kinetic energy into thermal energy. Car brakes are another example. When you brake, the kinetic energy of the moving car gets converted to thermal energy in the brake pads and discs. That's why they glow red hot after hard braking. The car's energy of motion has been dissipated as heat to the surroundings. Now let's talk about work. And no, We're not talking about the homework kind of work. Yeah. In physics, work has very specific meaning. Work is done when it first moves an object. And here's the crucial connection. The energy transfers equals the work done. The formula is beautifully simple. That is, work done equals force times distance moved in the direction of the force. That's pretty important. And the unit of work done is called joules, just like energy. When this weight lifter raises a 100 kg barbell 2 meters high, they're working against gravity, right? The force needed is about 1,000 newtons. That's equal to the weight of the barbell. So the work done is 1,000 newtons. That's the force multiplied by 2 meters. That's the distance moved in the direction of the force. That gives you 2,000 joules, or you can call that 2 kilojoules. That's exactly how much the gravitational potential energy store of the barbell increases. Sometimes the forces involved are enormous. Imagine pulling a 40-meter lorry across level ground. You would need about 2,000 newtons of force. If you somehow manage to pull it 40 meters, you'll do 80,000 joules of work. That's enough energy to power a typical home for about an hour or so. But what about friction? When you push a box across a rough floor, you're doing work against friction. That work doesn't increase the box's kinetic energy or potential energy stores. Instead, it's just dissipated to the surroundings as thermal energy. The box, the floor, and the surrounding air all get slightly warmer.